very special because if you can see,
Yeah.
the numbers all go to 11. Look, right across the board. 11,
Oh, I see.
11,
And most of
11, and
the
then
amps go up to 10.
Exactly.
Does that mean it's louder? Is it any louder?
Well, it's one louder, isn't it? It's not 10.
Alright everyone, welcome back to MedFlight Ultrasound Curriculum. Today we're going to talk about image optimization, which we're going to split into two parts. First we'll talk about the physics of how the image is created, and then we'll talk about the different knobs and sliders that you have to understand in order to generate your image. Last time we talked about how the Titanic disaster caused people to think about how to use sound waves in order to see faraway objects. But how are those sound waves actually emitted? Sound emission is based on the property of piezoelectricity. Some materials, like quartz crystals shown here, have this property, which means that when hit by an electrical current, they vibrate and emit sound waves. What's even better is that when the sound waves echo off of faraway objects, they bounce back, vibrate the crystal again, and convert that energy back into an electrical current. This is exactly what happens within an ultrasound transducer. Here in black and red is the crystal array of an ultrasound transducer activated by a voltage source. The transducer vibrates, sending out a sound wave. The voltage source is then disconnected, and the transducer is hooked up to an electrical current meter. During this time, it is listening for returning echoes. It spends a lot more time listening than sending and repeats the cycle 100 times per second, sending and then listening. It listens for predominantly two things. It listens for the time that the echo takes to come back, which is interpreted as the depth of an object, and the amount of sound reflection, referred to as the echogenicity of a tissue. To understand how this works, let's look at the sound waves themselves. During the sending portion, the sounds compress surrounding tissues, making a sound wave between areas of compression. The sound comes out, bounces off of tissues, and back to the transducer. The length of time it takes to bounce back from each organ is interpreted as the depth of the image on the screen. You'll also notice that the different organs in the image have different shades of gray. These shades of gray refer to the echogenicity of the tissue. By convention, fluids, like blood and water, are represented in black. These materials transmit sounds rather than echo them back, and are referred to as hypoechoic. On the other hand, other materials, like bones or stones, for example, echo or bounce back almost all of the sound they encounter. These materials are hyperechoic and are represented as bright white on the screen. Other tissues, like heart muscle and the liver, lie in between these two extremes. So let's go back to that image of the right upper quadrant we showed you earlier. Close to the transducer, in the near field, lies the hyperechoic skin and soft tissue of the abdominal wall, which took the least amount of time to echo back to the transducer. In the far field of the screen, we see the hyperechoic diaphragm, which took the longest time to echo the sound waves back to the transducer. And in the middle of the screen, you see the kidney, as well as the liver, which is relatively hypoechoic because it has a rich vascular supply and is full of hypoechoic blood. The last thing to discuss when talking about sound emission is the effect of wavelength on the image. Even though the speed of sound is constant, the frequency and wavelength of the emitted sound has a strong effect on the image itself. For example, the first transducer shown here is a high-frequency, short wavelength transducer, while the second one is a low-frequency, long wavelength transducer. They both get to the image at the same speed, but the shorter wavelengths are able to discriminate between closer objects, allowing for a high resolution. This is very important when, for example, you are placing an internal jugular line and want to avoid hitting a nearby carotid artery. Unfortunately, these waves lose their energy at shallow depths and can't penetrate deeper into the tissue. This is where the longer wavelengths of the low-frequency transducers shine. They allow for deeper penetration and visualization of the deeper abdominal organs. There are a number of different kinds of transducers, each with a different frequency range. For MedFlight, we've decided to start by acquiring the phased array transducer, which is more compact and allows for good imaging of the abdomen, heart, and lungs. So let's summarize how sound waves make an image. This is based on the principle of sound waves coming out and then bouncing back into the transducer and converting into an electrical current. The time it takes to do this is interpreted as the depth of an object, and each tissue has a different echogenicity represented on a gray scale. Resolution is a function of the transducer that you select, and in our case, this is the one thing that we currently can't adjust. Now we're going to talk about how to move the probe on the patient's body in order to get the best image you possibly can get. Let's talk about how you're going to get your ultrasound probe moves as good as Tom Cruise's dance moves in Tropic Thunder. First, you have to orient yourself with respect to the patient's anatomy. Next, you need to know how to move the probe in order to optimize the image. And finally, there are a few last-minute adjustments that you need to understand in order to optimize the view. Let's start with orientation. When you put the probe on the patient's body, you can be in a number of anatomic planes, similar to the ones you see when you read a CT scan. You can have long axis planes, like the sagittal or coronal axes, or the short planes of the transverse axis, which is what you're usually seeing when you scroll through a CT scan. Each probe has an indicator seen in gray here, and by convention, the indicator points to the head when you're in one of the long axis views, or to the patient's right side when you're in a transverse plane. You can think of the sound beam as an extension of the probe which slices through an anatomic plane. On the left you see a coronal view with the red dot oriented towards the patient's head, and on the right you see a transverse view with the red dot oriented to the patient's right hand side. Both views generate an image through that anatomical slice. When you actually see the image, you still have to do some mental gymnastics. For example, here is that right upper quadrant view, the way it will come up on your ultrasound screen on the left, compared to how it actually represents the slice through the anatomic plane. Imagine the green indicator pointing towards the head and the image rotated so that it slices through the organs. When you start out, you'll be getting used to flipping the image in your mind like this, but the more you scan, the better this gets. Next, let's talk about the probe movements. Once the probe is on the patient's body, you can move it in all kinds of directions in order to direct that beam to slice through the correct plane. Let's talk about each of these movements individually. First, you can slide the probe along its own axis, up and down like this. This is the first movement you will do in order to make sure that you are in the correct location. Sometimes you can further adjust the sliding movement by rocking the probe back and forth along its own axis. This can often help stay in the same rib space once you've found a good spot. Next, you can sweep through a tissue by moving the probe perpendicular to its axis. This will allow you to scan through the plane you're in this case the coronal plane. If you find a good rib space, sometimes you don't want to sweep anymore, and in this case you can fan the probe in order to scan through a plane. This is analogous to rocking the probe, but in the perpendicular axis. Finally, you can rotate between the planes in order to change from a long axis to a more short transverse axis. Let's summarize these movements. First, you find the area of interest by sliding and sweeping the entire probe. Next, you can optimize and survey that area by rocking and fanning the probe through an area of interest. This is usually where you're going to take your clip. Finally, you can change the plane of the image by rotating the entire probe along its own axis. Now that you know how to find the view with your probe, let's talk about how you're going to optimize this on the machine itself. There are two adjustments to be aware of. The first adjustment is called the gain. On the Lumify machine, this is just a slider in the bottom left hand of the screen. This adjustment will regulate how bright the image is by changing the dynamic range of the echogenicity. You want this adjustment to be bright enough that you can see all the echoes, but not so bright that everything looks whited out. The second adjustment is the depth. The ultrasound beam focuses in the middle of the screen, and this focal point gives you the best resolution. As a result, you want to adjust the depth of the image so that the area of interest is in the middle, but you're not wasting too much of the space on your screen. Depth adjustment is also done by a little scroll wheel in the left-hand side of the screen. To summarize, you can think of these adjustments as strategies to optimize the physics of how the image is generated. First, you optimize where your sound beam is going by moving the probe. Next, you can optimize the image itself by adjusting your gain to match the echogenicity of the surrounding tissues. Finally, you will optimize the depth by adjusting, shocker, the depth of the screen. The resolution for now can only be adjusted by changing the probe itself, but stay tuned, because newer ultrasound technology is on the way, and this might change pretty soon. No discussion of physics would be complete without talking about artifacts. Until now, we've simplified image formation as a simple sound comes out, bounces off an object, and comes back. While this is true, you know from grade school physics that waves can do some strange things when they pass through different media. For example, refraction causes this pencil to look broken when looking at it through the different media of air or water. Similarly, sound waves can refract, absorb, or scatter in addition to simply reflecting back from an object to the transducer. These different movements of the sound waves can produce artifact, which means that what you see on the screen isn't exactly the same thing as what is happening in the patient's body. Understanding how these form, however, allows us to properly interpret what is going on in the body based on the image we see. For example, when sound hits a stone or a bone, it will no longer be transmitted, and this will cause a shadow artifact. This is what happens when a rib gets in the way of your fast view, and you need to know how to get around it by moving your probe. On the other hand, when sound hits a fluid-filled organ like a bladder, a large fraction of the sound will get transmitted rather than bounce back. And this will cause enhanced brightness of the far-field organs, which you can see here on this view of the bladder on a fast exam. Finally, as sound encounters different media, for example a fluid-filled bladder, it can also get refracted around the edge, just like the example of the broken-looking pencil in the water beaker. This will cause bending and decrease transmission at the edge of the bladder, known as an edge shadow. This is important to understand, and distinguishing this shadow from free fluid will help you properly interpret your fast exam. As you can see, artifacts can throw you off, unless you understand how they form and anticipate their presence in your image. So that's it for physics and Knobbery. Today we talked about how the machine works, we talked about the three main adjustments of positioning your probe properly, but changing your gain and your depth, and we talked about the importance of various artifacts. Next time, we'll get to the fun part and talk about detecting free fluid, free air, and looking at the heart.
You're on 10 on your guitar. Where can you go from there? Where?
I don't know.
Nowhere, exactly. What we do is if we need that extra push over the cliff, you know what we do?
Put it up to 11.
11, exactly. One louder.
Why don't you just make 10 louder and make 10 be the top number and make that a little louder?
These go to 11.